Hi, I'm Autoencoders. In this video, I'll be presenting our work for the Zero Speech 2020 challenge entitled Vector Quantized Temporally Aware Correspondence Sparse Autoencoders for Zero Resource Acoustic Unit Discovery. This work is conducted as a collaboration of Boğaziçi University and National Defense University Naval Academy. I'll first talk about the goals of the challenge briefly and explain the evaluation metrics. Then I will introduce the methodology of correspondence sparse autoencoders we refer to as CORSA. I will then present this work's contribution on top of CORSA, which is the winner-take-all networks. Afterwards, I'll present our extension with the speaker adversarial training on the vector quantized CORSA network. Finally, I'll provide the experimental results depicting the improvements brought by every edition of this work. The task studied in this paper is the Zero Speech 2019 challenge, in which the participants are required to discover the inherent acoustic units in an unknown language in a completely unsupervised fashion. The defined metric for success is called ABX, where pairs of triphon sequences are given and they are compared using dynamic time warping. And this dynamic time warping is applied in the new latent space using several distance metrics, so that the ABX error and the bit rate are minimized simultaneously. The low bit representation of the speech is then used as pseudo-characters to reconstruct the speech. Hence, the task is called TTS without T. Since the task is unsupervised, the most intuitive approach is the autoencoder approach, in which we take the input and pass it through an encoder and then obtain a hidden layer activation space H, and I reconstruct the same thing using a decoder. We could very well use the hidden layer activation as the new latent space. The RSA, we call recurrent sparse autoencoder, tries to classify the activations of the encoder into the unknown set of acoustic units, what we refer to as the clustering layer. So the output of this layer, we refer to as P layer, is a posterior probability distribution of the unknown set of acoustic units. The sparsity of the activations of this layer is enforced with negative L2 norm, so that the P layer activations are like posterograms. In the correspondence RSA, CORSA, the corresponding subsequences of the speech are forced to generate each other. See, this is RSA and this is CORSA. The only thing that's changing is we're using X tilde instead of X, and these X tildes are obtained in a completely unsupervised fashion from the speech. This year, we added a version of the winner-take-all networks on top of the posterior layer to facilitate consistency in activations, making use of competitive learning. Our version of winner-take-all, we call temporal winner-take-all, uses excitatory and inhibitory weights in competitive learning and extends it to a sequence posterior transition, so that the corresponding states are excitatory following each time step, and other states are inhibitory in deciding current frames posterior. Similar to other works on this challenge, we apply a vector quantization layer right before the decoder, but this time vector quantization chooses the closest one-hot representation to p tilde, since we know that p tilde is nothing but a posterior activation. Furthermore, to make the encoder output speaker independent, we apply speaker adversarial training throughout a gradient reversal layer forked out of the encoder, so that the encoder is hopefully speaker independent. Just like our last year's work, we applied a medium filter based post-processing on quantized layer activations so that temporal continuity and better compression are obtained. In this medium filtering, misclassified activations are filtered out and triphones, hopefully, are obtained. This is an actual P layer activation or Q layer activation of a test utterance. Before we start looking at the experimental results, let's present some baselines. We obtain a rather low bit rate, we obtain a rather low ABX error with the raw features already, if we use PLP. But we see that the bits per second is quite high. So if we apply simple k-means on PLP, we reduce the bits per second, since we quantize the space into one of k centroids, but obviously ABX is increased. And we put the zero speech baseline, which is based on HMM with Dirichlet process priors, to provide a comparison, and it further reduces the bit rate, quantizes to deeper extent. RSA and Corsa results, which is our already presented last year's approach, exhibit the usage of the so-called clustering layer and the correspondence on training on both ABX and compression metrics. So this year's work, this year's contribution, winner-take-all network, provides a further improvement on both metrics, both ABX and bitrate. Vector quantization and speaker adversarial training provide improvements on ABX and compression, respectively. And if we apply post-processing on the quantized activations with medium filtering, it reduces the bit rate, and it reduces the bit rate with a little cost in the ABX. Obviously, when we apply medium filtering, some part of the actual activations are lost to obtain lower bitrate representation, and therefore it hurts the ABX performance a little bit. And it's also nice to compare the results of the proposed approach with the LVCSR based top line. We see that it's very similar to the top line. Obviously, this doesn't mean that we detected the actual characters or phonemes in the language, but it was nice that where we ended is very similar to the LVCSR based top line. This figure shows the plot of our system with respect to bitrate and AVX, and in comparison to the baseline, the top line, and other groups in 2019 and 2020 zero speech task. It can be seen that the performance of the Corsa 2020 hits very close to the top line, as we show in the previous table, and it's actually an outlier when compared to the other systems, and it's an outlier to the better direction, if you see that. And this figure shows the performance on the surprise language. It can be seen that we actually did a little bit too much of compression here. We would have got lower ABXs if we didn't compress so much this year when compared to our last year's result. And the top line is here, but still we can see that our approach can be an outlier compared to last year's and this year's other systems directions, other systems results. So in this work, we saw that sparse autoencoders are useful for acoustic unit discovery, and the proposed winner-take-all edition provides further improvements with the continuity and compression of the results. Also, vector quantization we also saw that the vector quantization can be applicable on binary space. This work was supported in part by the Scientific and Technological Research Council of Turkey, TÜBİTAK, under project 116E076 titled Keyword Search for Low Resource Languages. Thank you for listening, and we wish you healthy days. If you have any questions about the work, please feel free to contact us from the emails that we provide along with the paper. Thank you.